Number 1. Mosasaurus, the Meuse river jaw. Over 260 years ago, quarry workers in Maastricht, the Netherlands, pulled something enormous from the chalk limestone. It was a skull. Massive. Encased in the same sediment that locals had been carving into building stone for centuries. The year was 1764, and nobody had a word for what they were looking at. A cathedral canon named Theodorus Johannes Goding claimed the specimen. He believed it was important, though he couldn't say exactly what it was. Some naturalists who examined it declared it a whale. Others were certain it was a crocodile. Neither guess was remotely correct. Then, French revolutionary troops seized the fossil during the occupation of the Netherlands, making it one of the first custody battles over a fossil specimen in the history of science. That skull would eventually travel to Paris, where it caught the attention of Georges Cuvier. Cuvier's classification was shocking. He placed the creature within Squamata, the order that contains all living lizards and snakes. This was not a whale, not a crocodile. It was a marine reptile, and the scientific establishment of the late 18th century had no framework for such a thing. Today we call it Mosasaurus hoffmanni, and it remains one of the first marine reptiles ever formally described. Now here's where the classification debate gets interesting, because it still isn't settled. The mainstream position, supported by cranial bone articulation patterns, holds that mosasaurs are most closely related to monitor lizards, the family Varanidae. Think Komodo dragons. That's the conventional view, and it has strong anatomical backing. But a second camp argues for the snake lineage hypothesis. Researchers in this group point to shared derived features between mosasaurs and serpents, particularly jaw kinesis, the ability of the skull bones to flex and move independently during feeding. If you've ever watched a snake unhinge its jaw, you're looking at the same mechanical principle. A third, more fringe position suggests mosasaurs represent a completely independent squamate radiation, no close modern analog at all. A dead-end branch with no living cousins. After 260 years, molecular phylogenetics cannot resolve this because the fossils are simply too old for genetic material, and morphological analysis yields contradictory results depending on which character set you prioritize. What is not debated is what this animal could do. The skull of Mosasaurus hoffmanni was a feat of biological engineering. Rigid, overlapping frontal and parietal bones locked together with interlocking sutures. The entire structure designed to resist compression during biting. Each tooth measured over 3 inches, roughly 7.6 centimeters, with prismatic enamel surfaces for structural durability and fine serrations along the cutting edges for slicing efficiency. Bite force estimates place Mosasaurus between 13,000 and 16,000 pounds per square inch. To put that in modern terms, a saltwater crocodile, out for the most powerful bite among living animals, generates roughly 3,700 psi. Mosasaurus exceeded that by a factor of 4. Its sensory apparatus was equally specialized. Large eyes fitted with sclerotic rings, bony support structures inside the eyeball, gave it exceptional binocular vision. Yet brain endocasts reveal poorly developed olfactory lobes. This was a predator that hunted by sight, not by smell. Propulsion came from lateral tail undulation, a side-to-side swimming motion convergent with the way mackerel move through water. Estimated top speeds reached 30 miles per hour, or about 48 kilometers per hour. The flippers allowed high-speed maneuvering, but that performance came at a cost. Fossil flipper bones frequently show what paleontologists call separation injuries, stress damage from the sheer force of rapid directional changes, and then there's the violence, not against prey, against each other. Fossil evidence of intraspecific combat is abundant. Teeth embedded in jawbones, unhealed puncture wounds on cervical vertebrae. Territorial aggression was routine. Many of the combat victims are subadults or juveniles, which has led to the cannibalism hypothesis, larger adults actively hunting and consuming smaller members of their own species. The dietary record is confirmed by gut contents preserved in the fossils: bony fish, sharks, seabirds, turtles, other marine reptiles. One 75-million-year-old specimen was found with a 1-meter-long fish still in its stomach, dismembered during the attack. That's direct evidence of active predation, not scavenging. Carbon isotope signatures extracted from tooth enamel confirm frequent consumption of large sea turtles and giant marine reptiles, placing Mosasaurus at the absolute apex of the trophic pyramid. Its fossils have been recovered across tropical, temperate, and even subpolar zones. Canada, Europe, Africa, Antarctica. One of the most geographically widespread apex marine predators in the history of the planet. But Mosasaurus, for all its dominance, was confined to the reptilian body plan. What happens when you take the same apex marine niche and hand it to a fish, one with the single most powerful bite ever calculated for any animal? Number 2, Otodus Megalodon. The 40,000 psi bite. Its reign lasted nearly 20 million years. From roughly 23 million years ago to about 3.6 million years ago, Otodus Megalodon dominated every ocean on Earth. To appreciate the absurdity of that duration, consider that our entire genus, Homo, has existed for approximately 3 million years. Megalodon was the ocean's uncontested apex predator for nearly 7 times that long. Maximum size estimates place it at up to 24 meters, 78 feet callers in length. Weight estimates range between 50 and 70 metric tons. That's roughly 3 times the mass of a Mosasaurus. But the number that defines Megalodon above everything else is its bite force, 40,000 pounds per square inch, the single strongest bite force ever calculated for any animal in the history of life on Earth. The primary fossil evidence comes from teeth. Because the skeleton was cartilaginous, it doesn't preserve well. Those teeth are triangular, serrated, and measure over 7 inches, 18 centimeters, in vertical height. The jaw gape was roughly 2 meters wide, physically large enough to accommodate 2 adult humans standing side by side. Daily caloric demand has been estimated at approximately 100,000 kilocalories. In practical terms, that's equivalent to consuming an entire adult great white shark every single day. Megalodon has been classified as an ecologically versatile generalist. It targeted whales, seals, sea cows, and essentially any large marine vertebrate available. Its hunting tactics were not subtle. Fossil evidence from whale bones shows triangular gash marks concentrated on rib cages and chest cavities. The strategy was to strike large whale prey in the chest, puncture the ribs, and destroy internal organs. A front-loaded kill shot. Now, the taxonomy is contentious, and it matters because it changes how we reconstruct the animal's body. The mainstream theory places Megalodon as a macropredatory endothermic shark closely related to the great white lineage, the family Lamnidae. Under this model, body reconstructions are scaled from great white proportions. But a revisionist position argues that Megalodon actually belongs to a completely separate family, Odontocetidae, only distantly related to great whites. If that's true, then body reconstructions based on great white anatomy are fundamentally flawed. Some researchers now suggest Megalodon may have had a stockier, more whale shark-like profile, shorter, wider, and built differently than every museum model currently on display. Then there is the fringe theory, the one popular media loves, the deep ocean survival hypothesis. The idea that Megalodon descendants persist in abyssal zones undiscovered. It makes for compelling cinema. It is unsupported by any evidence. Ocean temperatures in the deep abyss are near freezing. A warm-blooded animal requiring 100,000 kilocalories per day cannot survive in an environment with virtually no large prey. The physics simply does not work. Recent thermoregulation studies suggest Megalodon possessed regional endothermy, partial warm-bloodedness, which would explain its ability to inhabit both tropical and temperate waters. And a breakthrough in zinc isotope analysis conducted on tooth enamel samples has definitively confirmed that Megalodon occupied the highest possible trophic level. It was eating the predators that ate the predators. Juveniles sheltered in shallow coastal nursery grounds, likely to avoid predation from larger adults and competing species. Growth rates were estimated as extremely slow, reaching sexual maturity over several decades, making population recovery from any decline extraordinarily difficult. Fossils have been found on every continent except Antarctica. A truly global distribution. Extinction came during the Pliocene, driven by declining populations of large baleen whales combined with significant ocean cooling. 100,000 kilocalories per day is a number that tolerates no disruption in supply. But before Megalodon disappeared, it shared its ocean with something unexpected, a dinosaur that had abandoned land entirely and walked into the river. Number 3, Spinosaurus. Walking into the river. Spinosaurus aegyptiacus reached 15 to 18 meters in length, 50 to 60 feet. That outclasses Tyrannosaurus rex in raw body length. Yet Spinosaurus was not built for the same world. It was built for water. Weight estimates fall between 7.5 and 9.2 metric tons, distributed on a forward-shifted center of mass that made bipedal terrestrial walking mechanically difficult. This animal's entire architecture leaned toward the riverine. The iconic dorsal sail, tall, thin, blade-shaped neural spines, created a structure roughly 2 meters high, visible even while the animal was partially submerged. What was the sail for? The mainstream theory holds it functioned as a species recognition display and sexual signal, analogous to a peacock's tail. An alternative theory suggests it was a thermoregulatory structure used to dissipate heat, similar to the sail of Dimetrodon, though this has largely fallen out of favor due to the thin blade-like cross-section. A fringe hypothesis proposes it was a hydrodynamic stabilizer or even a fat storage hump, like a camel's. No structural evidence supports that. The skull tells the real story. Long, narrow, crocodile-like. The snout was equipped with neurovascular openings functionally identical to pressure sensors found in modern crocodilian snouts. These structures detect water pressure changes caused by moving prey, an underwater detection system. The teeth were giant, slanted, and conical, designed to interlock when the jaws closed, creating a cage-like grip on slippery fish. In 2020, a landmark discovery confirmed what many had suspected. The tail was flexible and laterally flattened, with tall neural spines creating a fin-like paddle. Propulsion convergent with modern bony fish and newts, this animal could swim. The evolutionary steps leading to this body plan are remarkable. Bone density in Spinosaurus is abnormally high, lacking the internal marrow cavities found in most theropods. This is a feature seen in modern diving animals like penguins, dense bones providing ballast for submersion. The hind limbs were short and muscular, adapted for paddling rather than sprinting. The feet featured long, flat claws with possible webbing. Meanwhile, the forelimbs were massive, equipped with curved, blade-like claws suited for hooking large fish out of the water. Nostrils were positioned midway up the skull, allowing the animal to breathe, while most of the head remained submerged. Every feature points in one direction. Its primary diet consisted of giant Cretaceous coelacanths, particularly Mawsonia, which reached over 4 meters in length. The habitat was the fluvial river systems of what is now North Africa's Sahara Desert, the Kem beds of Morocco, approximately 95 million years ago. And here, a tragedy enters the scientific record. The original type specimen was described by the German paleontologist Ernst Stromer in 1915 and housed in Munich's Bayerische Staatssammlung. Stromer had pleaded with the museum director to move the fossils to safety as the war intensified. His requests were denied for political reasons. On April 24, 1944, Allied bombing destroyed the museum and the specimen with it. One of paleontology's greatest losses. The bipedalism debate persists to this day. Was Spinosaurus a facultative quadruped on land, or did it essentially never leave the water? Computational models published in 2022 remain split. What is clear is that Spinosaurus represents the most radical departure from the standard theropod body plan ever documented, a dinosaur that convergently evolved toward a crocodile-like lifestyle. And speaking of crocodiles, what about an actual crocodilian that hunted dinosaurs? Number 4. Deinosuchus. The terrible crocodile at the water's edge. Deinosuchus reached 12 meters in length, 39 feet, making it one of the largest crocodilians in the entire fossil record. Mass estimates range from 8.5 to 15 metric tons. At the upper end, that's heavier than any known Tyrannosaurus rex specimen. The bite force has been estimated to exceed 23,000 pounds per square inch. Bone-crushing capability far beyond any modern crocodilian. The skull alone reached 1.5 meters, roughly 5 feet, approximately the height of a modern adult human. Its back was protected by thick hemispherical osteoderm armor plates embedded in the skin. Biological body armor. Its preferred habitat was estuarine and brackish water bays along the coastlines of Cretaceous North America. And here's the forensic evidence that makes Deinosuchus extraordinary. Bite marks precisely matching Deinosuchus tooth dimensions have been found on the bones of Albertosaurus and Apalachiosaurus. This was a confirmed dinosaur killer. The hunting strategy was classic ambush predation at the water's edge, lunging to seize large terrestrial prey, dragging it underwater to drown. Identical to modern crocodile behavior, but scaled up enormously. The snout morphology was broad and robust, most similar to a modern American alligator rather than a slender gharial, designed for a crushing grip rather than fish snatching. The teeth were massive and thick-crowned, built for crushing shells and bones rather than piercing and slicing. Estimated lifespan reached up to 50 years, and unlike modern crocodilians, which slow growth dramatically after maturity, Deinosuchus appears to have maintained a high growth rate throughout its life. Fossils have been recovered across 10 U.S. states and northern Mexico. Remarkably widespread. Western specimens consistently reach significantly larger body sizes than their eastern counterparts, suggesting regional ecological differences driven by prey availability or climate. Phylogenetically, Deinosuchus diverged before the last common ancestor of modern alligators and crocodiles. It is not a direct ancestor of anything alive today. The mainstream theory holds that Deinosuchus achieved its size through prolonged growth periods in highly productive wetland ecosystems. An alternative theory suggests gigantism was driven by arms race dynamics with co-occurring large theropod dinosaurs, size as a direct competitive response. A fringe position speculates that modern deep swamp crocodilians in Africa could approach similar sizes under the right conditions. No evidence supports this. Prey included giant sea turtles, dinosaurs of all sizes, and large fish. A true generalist apex predator. Its temporal range spanned 82 to 73 million years ago, overlapping with the final chapter of the Age of Dinosaurs. One of the last giant crocodilians before the KPG extinction swept it away. But while Deinosuchus ruled the shorelines, something was happening far offshore. A whale unlike any alive today was learning to bite back. Number 5. Livyatan melvilli. The whale that bit back. The name alone tells you what the scientists thought of it. Livyatan melvilli, named after Herman Melville, author of Moby Dick. A deliberate homage to the most famous literary whale, reflecting this animal's status as perhaps the most fearsome cetacean that ever lived. Length estimates place it between 13.5 and 17.5 meters, 44 to 57 feet. They were comparable in size to a modern adult sperm whale. Maximum weight reached roughly 50 metric tons, matching Megalodon at the upper range. But here's the critical distinction. Livyatan possessed the largest functional biting teeth of any known animal, individual teeth reaching 36 centimeters, over 14 inches in length. Unlike modern sperm whales, which have teeth only in the lower jaw, Livyatan had massive functional teeth in both upper and lower jaws. A dual jaw dentition built for one thing: killing. The skull featured a large supracranial basin spanning the entire length of the snout, likely housing a massive spermaceti organ. What did it do? The mainstream theory says echolocation and buoyancy control, as in modern sperm whales. An alternative theory proposes the organ was adapted for aggressive head ramming during intraspecific combat or prey stunning, a biological battering ram. The fringe interpretation suggests focused acoustic blasts from the spermaceti organ to disorient prey. No physical evidence supports this mechanism, but it captures something real about the sheer lethality this animal projected. Livyatan's diet consisted primarily of small to medium baleen whales. This was a confirmed raptorial predator of other cetaceans. Its hunting strategy relied on inflicting deep wounds and tearing flesh with those massive teeth, entirely unlike the suction feeding of modern sperm whales. The skull architecture was shorter and more robust than its modern relatives, adapted to accommodate the enormous jaw-closing musculature required for macropredation. Teeth were protected by unusually thick enamel, a primitive feature lost in most modern toothed whales. Its temporal range was approximately 13 to 12 million years ago during the Middle Miocene. Primary habitat: coastal waters around what is now Peru, the Pisco Formation, one of the richest marine fossil sites on Earth. And here's the matchup that captures the imagination. Livyatan coexisted directly with Otodus Megalodon in the same waters, two apex predators of roughly equivalent size competing for the same whale prey. Even juvenile specimens show teeth with open pulp cavities at massive dimensions, indicating that Livyatan was already enormous before reaching full maturity. The evolutionary steps leading to this predator involved a dramatic divergence from the suction-feeding body plan that characterizes most modern toothed whales, back toward the active macropredatory strategy of much earlier marine reptiles. Extinction came with global cooling during the late Miocene, which reduced baleen whale diversity and shifted prey populations beyond Livyatan's coastal hunting range. The ocean got colder, the food moved, and a 50-ton whale with 14-inch teeth couldn't follow it. Now let's go back to land and meet a predator that made Tyrannosaurus look slow. Number 6. Giganotosaurus carolinii, the slash and bleed killer. Giganotosaurus reached 12 to 13 meters in length, 40 to 43 feet, potentially exceeding Tyrannosaurus rex in overall body length. It was the largest land predator of Cretaceous South America. Mass estimates settle around 8 to 8.5 metric tons, slightly lighter than the heaviest T-Rex specimens. But here's the number that matters most. Bite force. Estimated at only 6,000 to 13,000 newtons. Tyrannosaurus rex generated roughly 60,000 newtons. Giganotosaurus had a fraction of the jaw power, and yet it was no less lethal. The difference is strategy. Where T-Rex was a bone crusher, Giganotosaurus was a blade. Its teeth were finely serrated along both edges, designed to slice through flesh and cause catastrophic bleeding rather than pulverize bone. The skull was long and narrow, reaching up to 1.6 meters, shaped for rapid lateral slashing motions rather than the deep compressive bites of Tyrannosaurs. Well-developed olfactory bulbs indicated a keen sense of smell, potentially used to track wounded, bleeding prey over long distances. Inflict a wound. Wait. Follow the blood. The arm structure tells a parallel story. Three-fingered forelimbs significantly longer and more functional than T-Rex's vestigial arms. Equipped with sharp, hooked claws for gripping prey while delivering slashing bites, Giganotosaurus kept its tools. A lower center of gravity and more streamlined build likely made it faster and more maneuverable than T-Rex, and brain-to-body ratio was significantly smaller, suggesting less sophisticated cognitive abilities and more reliance on instinct. The mainstream theory holds Giganotosaurus was a solitary ambush predator that used hit-and-run tactics against large sauropods, inflicting wounds and trailing prey as it weakened. The alternative theory is more dramatic, pack hunting. Multiple individuals coordinating attacks on giant sauropods like Argentinosaurus, which weighed over 70 metric tons. Some researchers argue that no solo predator of 8 tons could realistically bring down a 70-ton sauropod. Cooperative hunting is the only mathematically viable explanation. A fringe position proposes Giganotosaurus was primarily a scavenger, using its speed to steal kills from smaller predators. The bite force data arguably supports this, but the tooth morphology does not. Habitat: humid floodplains of late Cretaceous Patagonia, Argentina, approximately 97 million years ago. The most complete skeleton, specimen MUCPV-CH1, is roughly 70% complete, providing detailed biomechanical data. Giganotosaurus went extinct approximately 30 million years before the KPG asteroid event, likely due to shifting climate patterns and declining sauropod prey populations. It demonstrates something fundamental. Raw bite force is not the only evolutionary path to apex status. Speed, blade-like dentition, and slashing mechanics represent an entirely parallel predatory paradigm, but every predator so far has been bound to the surface, land, or water. What happens when the apex predator takes to the air? Number 7. Quetzalcoatlus Northropean, the living airplane. Wingspan 10 to 12 meters, 33 to 39 feet. Comparable to a small Cessna aircraft, the largest confirmed wingspan of any flying animal that has ever existed. Standing on the ground, Quetzalcoatlus reached approximately 3 meters tall as a modern giraffe. And despite these dimensions, body mass was only 200 to 250 kilograms. That's the paradox. The weight savings came from hollow pneumatic bones, and extensive air sac systems that kept mass radically low. Internal bone structure featured thin walls reinforced with cross struts. Engineering optimized for minimum weight with maximum structural integrity. The beak was long, toothless, and needle-sharp, reaching 2 meters in total length. A precision instrument. The neck was stiff and elongated with limited range of motion, structurally constrained more like a lance than a flexible serpent neck. Terrestrial locomotion was quadrupedal. Quetzalcoatlus walked on its wing fingers as front legs, a gait unique to pterosaurs. The takeoff mechanism was equally unusual, a quadrupedal launch, pushing off simultaneously with both arms and legs to generate the initial lift needed for a 250-kilogram body. This bypasses the bird-style running takeoff entirely. Research led by biomechanist Michael Habib demonstrated that this launch strategy was not only viable, but necessary. No runway required. Flight style was static soaring on thermal and wind currents. Sustained flapping flight was likely impossible or extremely limited at this body mass. Wing aspect ratio measured 8.1, nearly identical to modern storks and eagles, confirming long-distance soaring capability. The wing membrane, the brachiopatagium, stretched from the enormously elongated fourth finger all the way to the ankles. A single continuous flight surface. The body was covered in pycnofibers, hair-like filaments providing insulation, suggesting endothermic or near-endothermic metabolism. What did it eat? Here, the theories diverge sharply. The mainstream theory, championed by paleontologist Mark Whitten, holds that Quetzalcoatlus was a terrestrial stalker, hunting on foot like a giant stork, snatching small prey from the ground with its lance-like beak. Forward-facing eyes suggest good stereoscopic depth perception, essential for precision ground strikes while walking. An alternative theory proposes skim feeding, flying low over water surfaces, and dipping the beak to catch fish, similar to modern skimmers. This has been largely rejected due to neck stiffness and the fact that its habitat was inland, far from coastlines. A fringe hypothesis suggests it was an aerial predator, swooping down from height to snatch prey in flight. Wing loading calculations show it simply could not generate the required lift-to-weight ratio for dive-and-grab maneuvers. Diet likely consisted of baby dinosaurs, small mammals, large insects, and small reptiles. A generalist ground forager. Habitat: inland semi-arid floodplains of late Cretaceous North America, far from any coastline. Discovered in the Javelina Formation of Big Bend, Texas, it lived until the very end of the Cretaceous 66 million years ago, among the last pterosaurs, dying in the KPG extinction. But to understand where jawed predation itself began, we need to go much further back 360 million years to a fish that had no teeth at all. Number 8. Dunkleosteus terrelli, the Devonian war machine. Dunkleosteus terrelli was a placoderm, an armored fish from an entirely extinct class of vertebrates that dominated the Devonian seas 360 million years ago. This is the oldest predator on this list by a vast margin. Size estimates range from 6 to 10 meters, 20 to 33 feet. The unchallenged apex predator of its era. Weight fell between 1 and 3 metric tons. Modest by later standards. Enormous for the Devonian. And here's what makes Dunkleosteus biomechanically unique among every predator in this entire series. It lacked true teeth entirely. Instead, it used self-sharpening bony shearing plates that functioned as cutting blades. Every time the jaw opened and closed, the upper and lower bony plates rubbed against each other, maintaining razor-sharp edges through constant use. A biological self-honing system, no maintenance required. Jaw opening speed was approximately 20 milliseconds, already fast enough to create a vacuum suction force that actively pulled prey into the mouth. Jaw closing speed was roughly 60 milliseconds. That combination, suction feeding plus a powerful crushing bite, delivered in a single strike. Bite force measured 5,300 newtons, approximately 1,200 pounds, concentrated at the rear dental plates. The highest calculated for any Devonian organism. The craniokinesis was powered by a 4-bar linkage mechanism. This is a mechanical system where 4 rigid bone elements rotate around joints, allowing the upper jaw to swing upward while the lower jaw drops simultaneously. Modern engineers use 4-bar linkages in everything from car suspensions to robotic arms. Dunkleosteus evolved at 360 million years ago. The mainstream theory holds Dunkleosteus was a slow, powerful pursuit predator that relied on armored durability and crushing bite to overpower any prey. An alternative theory argues it was primarily a vacuum ambush feeder. The 20 millisecond gape speed suggests it inhaled prey at close range rather than chasing it down. A fringe hypothesis proposes it may have been partially warm-blooded to sustain the metabolic demands of active predation at its size, though no direct physiological evidence exists. The head and thoracic region were encased in thick bony plates, a biological tank from the neck forward. Behind the armor, the rest of the body was cartilaginous, reconstructed with a blunt, shark-like profile based on hydrodynamic modeling. Prey included other armored placoderms, primitive sharks, and ammonites. Nothing in the Devonian was safe. The combination of high opening speed and massive closing force in the same jaw is biomechanically unique. No other known vertebrate achieves both simultaneously. First discovered in the Cleveland Shale Formation of Ohio. Phylogenetically, this animal is significant far beyond its own era. Placoderms are the sister group to all other jawed vertebrates. Dunkleosteus sits near the base of the evolutionary tree that produced every shark, bony fish, amphibian, reptile, bird, and mammal alive today. It was eliminated by the Hagenberg event at the Devonian Carboniferous boundary, one of the major mass extinctions that wiped out all placoderms worldwide. A predatory engineering solution, self-sharpening blades, vacuum suction, armored defense that evolution explored once and never repeated. Now fast forward 300 million years, the dinosaurs are gone, the asteroid has done its work, and in the steam and heat of the Paleocene, something enormous is coiling in the river. Number 9, Titanoboa cerrijonensis, the post-dinosaur apex. Titanoboa cerrijonensis reached 12.8 to 14.3 meters, 42 to 47 feet. The longest snake ever documented in the fossil record. Weight, approximately 1,135 kilograms, or 1.25 metric tons. Heavier than a modern grand piano. Maximum body width at its thickest point, approximately 1 meter. Wider than a standard doorway. It appeared just 6 to 8 million years after the asteroid wiped out the non-avian dinosaurs, roughly 60 to 58 million years ago. That timeline matters. Timeline. The KPG extinction cleared every large predator niche on the planet. Titanoboa was among the first animals to fill the vacuum. Classified within the Boidae family, boas, not pythons, it represented an extinct giant boid lineage with no living descendants at this scale. Its habitat was the world's earliest tropical rainforests, in what is now the Cerrejón coal mine region of northeastern Colombia. And because Titanoboa was cold-blooded, its gigantic size was only physiologically possible in extreme heat. This is where the animal becomes a scientific instrument. Its existence serves as a direct thermometer for Paleocene climate. The mainstream theory, advanced by paleontologist Jason Head and colleagues, uses the ectotherm body size to temperature scaling relationship to calculate that mean annual temperatures in Titanoboa's habitat must have been 30 to 34 degrees Celsius, significantly warmer than today's tropics. An alternative theory suggests Titanoboa may have had a slightly elevated metabolic rate compared to modern boas, meaning temperature estimates derived from its size could be 2 to 3 degrees too high. A fringe hypothesis points to atmospheric oxygen levels, arguing that higher oxygen in the Paleocene independently enabled gigantism regardless of temperature. The evidence is mixed. Titanoboa was primarily piscivorous, hunting large lungfish and catfish in murky river systems. Similar to a modern green anaconda, but at triple the scale. The hunting strategy was semi-aquatic ambush, lying in wait in shallow, turbid water and striking prey with explosive lateral lunges. Constriction force was likely equivalent to several times its 1.25-ton body weight, sufficient to crush the ribcage of any Paleocene vertebrate. The teeth were small and backwards curving, designed to grip prey and prevent escape before the coils engaged. Not for cutting, not for chewing, not... Locomotion on land was extremely sluggish, estimated at roughly 1 mile per hour, making it almost exclusively an aquatic hunter. It could remain completely concealed in murky river water with only its nostrils above the surface, virtually invisible. The skull remains almost entirely unknown. All ecological inferences about feeding mechanics come from vertebral morphology and phylogenetic comparison with modern boas. It competed with the large crocodilomorphs like Cerrijonensis for the apex freshwater predator niche. Titanoboa filled the ecological vacuum left by the extinction of marine and freshwater reptilian predators, demonstrating how quickly evolution scales up body size when apex niches open. But Titanoboa wasn't the only giant lurking at the water's edge. Millions of years earlier, on another continent, something even heavier was waiting in the current. Number 10. Sarcosuchus imperator, the super croc of the Sahara. Sarcosuchus imperator reached at least 11 to 12 meters in length, 36 to 40 feet, twice the length and 10 times the weight of the largest modern Nile crocodiles. Weight, approximately 8 metric tons, comparable to a large African elephant. The skull alone measured nearly 1.6 meters, 5.2 feet, the size of a full-grown adult human from head to toe. Bite force. An estimated 8 tons of force, or 16,000 pounds, exceeding the bite force commonly attributed to Tyrannosaurus rex. The jaws contained 132 stout conical teeth, smooth-crowned, optimized for gripping and crushing rather than slicing. And then there's the feature found in no modern crocodilian, a narial bulla. A bulbous growth at the tip of the snout. What was it for? The mainstream theory holds it functioned as a resonance chamber for producing low-frequency calls across river territories. An alternative theory proposes it increased grip strength at the snout tip, allowing Sarcosuchus to hold thrashing dinosaur prey more securely. Structural analysis supports this. The fringe hypothesis suggests it was an enhanced olfactory chamber, giving Sarcosuchus an unusually acute sense of smell for detecting prey in murky water. No neurological evidence is available to confirm any of these. The body was encased from head to tail in overlapping bony scutes, armor plates providing protection even against theropod teeth. Habitat: fluvial river environments in what is now the Gadufawa region of Niger. During the early Cretaceous, approximately 112 million years ago, this was a lush, vegetated river system. Diet was generalized. Large vertebrates including giant fish, turtles, and mid-sized dinosaurs that ventured to the water's edge. Hunting tactic: classic ambush specialist. Lying submerged in murky water before lunging with explosive speed to seize prey and drag it under to drown. Short, powerful legs with sharp claws gripped slippery riverbanks, functional for brief terrestrial lunges but not sustained land movement. The massive, muscular tail provided rapid acceleration bursts in water, the primary propulsive organ for the initial attack strike. Sarcosuchus reached its maximum size over an extraordinarily long lifespan of 50 to 60 years, confirmed by growth ring analysis from osteoderm cross-sections. Continuous growth, never stopping. It competed directly with giant theropods like Carcharodontosaurus, both apex predators sharing the same North African river ecosystem. Phylogenetically classified as a crocodilomorph, a distant relative of modern crocodiles, but not a direct ancestor of any living species. Fossils were first described from the Gadufawa deposits by French paleontologist Philippe Taquet, from the same formations that yielded Nigersaurus and other remarkable Cretaceous fauna. 10 predators, spanning 360 million years, different lineages, different continents, different eras. Yet the similarities between them are not coincidental. They are inevitable. Convergent engineering: how evolution built the same predator. Twice. Consider the pairing Deinosuchus and Sarcosuchus, separated by 30 million years and an ocean. Both converged on nearly identical body plans, 12-meter ambush crocodilians with bone-crushing bites and osteoderm armor. Both occupied the same ecological niche, river and estuarine apex ambush predator, despite having no direct evolutionary relationship to each other. Mosasaurus and Livyatan, a marine reptile and a marine mammal, both evolved massive jaws, binocular vision, and active pursuit predation of large marine vertebrates. Separated by approximately 53 million years, yet both achieved roughly equivalent body sizes of 13 to 18 meters and apex trophic positions. Giganotosaurus and Tyrannosaurus rex, contemporaneous on different continents, both reached 12 to 13 meters but evolved completely different killing strategies. Slicing versus crushing. The same job, different tools. The mainstream interpretation is that convergent evolution is driven by identical physical constraints. Hydrodynamics, structural mechanics, and energy budgets produce a limited number of viable solutions for apex predation. An alternative interpretation frames it through ecological opportunity theory. When an apex niche opens, the first lineage to fill it will be shaped into a predictable morphotype regardless of ancestry. The fringe view invokes deep homology, the same ancient genetic toolkit reactivated across unrelated lineages, making convergence less coincidental and more structurally predetermined. Dunkleosteus' self-sharpening bony plates have no analog in any later predator, a unique solution that evolution explored once and abandoned after the Devonian. Quetzalcoatlus likewise has no true convergent partner. No other lineage has ever produced a 10-meter flying terrestrial stalker. Some niches, it seems, are only accessible once. The ambush from water strategy appears in Mosasaurus, Deinosuchus, Sarcosuchus, Titanoboa, and Spinosaurus, 5 unrelated lineages across 300 million years, all converging on the same tactic. Bite force shows a clear escalation across geological time. Thermoregulation strategies converge as well. Megalodon's regional endothermy, Spinosaurus's dense bones for aquatic thermal regulation, Titanoboa's absolute dependence on ambient temperature, multiple approaches to the same metabolic challenge. The consistent pattern of gigantism across all 10 predators correlates with ecosystem productivity. Stable, energy-rich environments reliably produce larger apex predators. This convergence pattern suggests that if apex marine and terrestrial niches reopened today under equivalent conditions, evolution would likely produce recognizably similar predators again. The extinction cascade, how apex predators fell. Mosasaurus, Quetzalcoatlus, and Deinosuchus all perished in the KPG extinction event 66 million years ago, a single asteroid erasing 3 of the 10 predators simultaneously. But the impact didn't kill them directly. It collapsed primary productivity. The photosynthesis shutdown cascaded up the food chain over months to years. The base of the pyramid crumbled and everything above it followed. Megalodon's extinction 3.6 million years ago was driven by a fundamentally different mechanism. Pliocene ocean cooling reduced large baleen whale populations. 100,000 kilocalories per day became unsustainable. Livyatan disappeared earlier around 12 million years ago from the same general mechanism, ocean cooling and shifting whale diversity, but triggered by Miocene rather than Pliocene climate changes. Giganotosaurus went extinct roughly 97 million years ago, 30 million years before the asteroid, likely due to regional climate shifts and declining sauropod populations. Dunkleosteus was eliminated by the Hangenberg event at the Devonian Carboniferous boundary approximately 360 million years ago, an extinction that wiped out all placoderms globally. Spinosaurus disappeared around 95 million years ago as North African river systems changed and its specialized fish prey declined. Titanoboa vanished when Paleocene tropical temperatures dropped below the 30°C threshold its ectothermic metabolism required. Temperature was the direct kill mechanism. Sarcosuchus's extinction around 100 million years ago correlates with ecosystem restructuring across North African fluvial systems. The mainstream theory holds that apex predators are inherently extinction-prone because they require the largest territories, the most calories, and the most stable ecosystems. Any disruption at the base of the food chain hits them first and hardest. An alternative theory suggests extinction selectivity is driven by metabolic flexibility. Species with narrow thermoregulatory ranges or obligate high caloric demands are most vulnerable regardless of apex status. The fringe position proposes that mass extinctions disproportionately target large-bodied species through a size filter above a certain mass threshold. Survival probability drops dramatically regardless of ecological niche. The vulnerability paradox is this. The very specializations that made each predator dominant became lethal liabilities when conditions shifted. Megalodon's size demanded 100,000 kilocalories per day. Titanoboa depended on extreme heat. Spinosaurus was locked into fish specialist anatomy. A 50-ton megalodon required roughly 250 times more daily energy than a 200-kilogram great white shark. Even a 10% decline in prey availability becomes catastrophic at that scale. Deinosuchus's 50-year lifespan and slow reproductive rate meant population recovery from any decline was desperately slow. None of the 10 survived long after their primary prey base diminished. Modern parallel, today's large apex predators, orcas, great whites, tigers, face-analogous pressures from habitat loss and prey decline. The same extinction mechanics operating on shorter timescales. The fossil record shows that apex gigantism is always temporary. Every era's largest predator is eventually replaced, usually within 5 to 20 million years, but the apex niche itself is reliably refilled by entirely different lineages. After mosasaurs, marine mammals rose. After giant crocodilians, smaller species persisted. Apex predation is an ecological role that the biosphere consistently demands. No single lineage holds the position permanently. The forensic record, reading violence in bone. Paleontological forensics is the study of trace fossils, bite marks, gut contents, tooth impressions, and bone pathologies. It provides direct behavioral evidence that no skeleton alone can offer. Consider Deinosuchus. Bite marks found on Albertosaurus and Appalachiosaurus bones match the tooth spacing, depth, and curvature of Giganotosaurus dental arcades with statistical precision. These marks prove active attack, not scavenging. Bone remodeling patterns show the prey survived the initial bite. The prey walked away, injured but alive, and the bone healed around the wound. Megalodon's signature is equally distinctive. Deep triangular gashes on fossilized whale bones matching the exact serration pattern and tooth width of Otodus Megalodon teeth. The targeting pattern is consistent. Whale rib cages and pectoral regions show the highest concentration of bite marks, confirming the chest strike hunting hypothesis. Mosasaurus intraspecific violence leaves perhaps the most visceral evidence. Fossilized jawbones with competitor teeth still embedded in the bone matrix, animals that were bitten and never shed the embedded tooth before death. Unhealed cervical puncture wounds suggest that some territorial fights were fatal. The animal died from the injury before any bone healing could begin. The mainstream interpretation treats these traces as normal territorial and cannibalistic behavior in a dense predator population. An alternative interpretation notes that the frequency of intraspecific injuries in Mosasaurus is abnormally high compared to modern marine predators, suggesting unusual population stress or resource scarcity. A fringe view proposes ritualized combat rather than lethal intent. The embedded teeth and neck wounds are accidents during dominance displays, not genuine attempts to kill. Zinc isotope analysis of megalodon teeth confirms it occupied the absolute highest trophic level available, a chemical signature that requires consuming other apex predators. Livyatan's tooth enamel thickness, unusually heavy for a toothed whale, is interpreted as an adaptation to resist fracturing during violent prey struggles. Giganotosaurus's slash-and-bleed strategy is inferred entirely from tooth morphology, serrated, blade-like, combined with the absence of bone-crushing adaptations. Sarcosuchus' teeth are smooth-crowned and lack interlocking fit, forensic evidence that its killing method was grip and drown rather than bite and shear. Spinosaurus tooth marks have been found on large coelacanth bones in the chem beds, conical puncture marks matching Spinosaurus tooth cross-sections. Every apex predator on this list left identifiable damage signatures, unique bite profiles as distinctive as fingerprints, turning bones into crime scenes, what modern science still doesn't know. The monitor lizard versus snake debate for Mosasaurus remains unresolved after 260 years. Molecular phylogenetics cannot be applied to fossils this old. Megalodon's body shape depends entirely on which family it belongs to. If every museum model is based on great white proportions and Megalodon was actually an ododontid, every reconstruction on the planet is wrong. Spinosaurus locomotion models from 2020 and 2022 disagree on whether it was an obligate aquatic swimmer or a wading bipedal fisher. The answer changes its entire ecological interpretation. Coloration is unknown for every single predator on this list. No preserved pigment structures have been confirmed for any of the 10 species. Vocalization. Did Sarcosuchus use its narial bulla to produce territorial calls? No preserved soft tissue or neural pathway data exists. Quetzalcoatlus flight mechanics remain an active biomechanical debate, whether it could sustain any powered flapping at all, or was entirely dependent on thermals and ridge lift. Livyatan's spermaceti organ function is inferred entirely from the bony basin in the skull. The organ itself is never preserved. Echolocation, ramming, buoyancy, all speculative. Dunkleosteus' body posterior to the thoracic shield is entirely unknown. Every reconstruction of its tail, fins, and swimming mechanics is hypothetical. The mainstream view holds that emerging technologies, synchrotron micro-CT scanning, ancient protein analysis through paleoproteomics, and computational fluid dynamics are progressively narrowing these uncertainties. An alternative view acknowledges the fundamental limitations of the fossil record. Soft tissue rarely preserves, behavior cannot be directly observed, and many questions are permanently unanswerable. The fringe position suggests future recovery of ancient DNA from younger specimens like Megalodon or Livyatan could theoretically resolve phylogenetic and physiological questions, though most molecular biologists consider this extremely unlikely given degradation. Timescales. Titanoboa's skull remains almost entirely unknown. Giganotosaurus. Pack hunting has no direct evidence, no bone beds, no trackways. Deinosuchus' salt tolerance is based on geographic distribution, not physiological evidence. Growth rates for most of these predators are estimated from bone histology, counting growth rings, Sauk, a method that assumes consistent annual deposition, which is not guaranteed. Megalodon's thermoregulatory status fundamentally changes estimates of its metabolic rate, daily caloric needs, and geographic range. The intelligence of every predator on this list is poorly constrained. Brain endocasts provide volume estimates but cannot reveal neural organization. Spinosaurus' original type specimen, destroyed in 1944, may have contained anatomical details never recorded in Stromer's notes. Information permanently lost. Whether Megalodon and Livyatan actively competed, partitioned their prey, or avoided each other entirely is unknown. The coexistence is confirmed. The interaction dynamics are pure inference. Every reconstruction of these predators, in museums, documentaries, and scientific papers, represents a hypothesis, not a confirmed reality. Every predator on this list, across 360 million years, 5 continents, and a dozen unrelated lineages, was built within the same physical constraints. Jaw mechanics obey the same lever principles in Dunkleosteus and Megalodon, separated by 300 million years. Hydrodynamics shaped Mosasaurus' tail, Spinosaurus' paddle, and Livyatan's fluke into convergent solutions for the same propulsion problem. Structural engineering limits explain why Quetzalcoatlus couldn't exceed 250 kilograms and still fly. Thermodynamics governed Titanoboa's existence as directly as any physical law. Caloric mathematics killed Megalodon as surely as any predator. These were not random monsters. They were engineering solutions refined by natural selection within the non-negotiable boundaries of physics. The same forces that shaped them still operate today, on smaller organisms, in changed climates, but under identical physical laws. The fundamental laws of nature do not create monsters. They constrain life into predictable shapes. And those shapes, when scaled to their maximum, are what we call monsters.